In the last video, we talked about quantum measurements. We saw that measurable quantities are represented by operators, and for spin 1/2 nuclei, the operators that we care about are the Ix, Iy, and Iz spin angular momentum operators. These operators tell us about the spin components along the x, y, and z directions. Knowing this now, we must raise an important question. Can we measure all of those spin components at the same time? As in, can a spin 1/2 nucleus have a definite x component, a definite y component, and a definite z component all at once? And classically, we'd probably say yes. If I had a normal arrow in 3D space, like this one here, I can describe it by giving you its x, y, and z components. Let's say 3, 9, and 5. There's nothing mysterious about that. The arrow has projection along x, it has projection along y, and it has projection along z. So if spin were literally a tiny classical arrow, then measuring Ix, Iy, and Iz at the same time would not be a problem. But quantum spin is not a classical arrow, and this is where commutation relationships become important, because with those three angular momentum spin operators, they will not work together. Back when you learned multiplication, commutation questioned if 3 times 5 was the same thing as 5 times 3, and it is. You get 15 both ways. Here, commutation tells us whether two operators are compatible. And by compatible, I mean whether the corresponding observables can have definite values at the same time. Now, commutation isn't always true here. So let's build that idea slowly. Suppose we have two operators, A and B. We can apply them to a state in one order, A, B on psi. This will mean that B acts first and then A acts second. But we could also apply them in the opposite order, B, A on psi. This means A acts first and then B acts second. Now the key question is, do these two orders give the same result? If they do, then AB on psi would be equal to BA on psi. This means applying B first and then A to psi would give the same final state as applying A first and then B. So the order does not matter here. Now if we want to test whether these two results are the same, the most natural thing to do is subtract them. If two things are equal, then their difference should be 0. So we take AB on psi and we subtract BA on psi. If this gives 0, then for every possible state, the two orders always produce the same result. So we can write AB minus BA acting on psi is equal to 0. And since this has to be true for any state, the operator inside the parentheses must be the 0 operator. And that difference is what we call a commutator. So we can define it as the commutator of A and B is equal to AB minus BA. And this definition is not random. It's literally measuring the difference between doing the operators in one order versus doing them in the opposite order. So if the commutator between A and B is equal to 0, then the difference between AB and BA would be equal to 0, which would mean that AB is equal to BA. So the operators commute and the order does not matter. But if the commutator of A and B is not equal to 0, then that would mean AB does not equal to BA. So the order does matter here. Applying A then B does not give the same result as applying B then A. If two measurement operators commute, then they are compatible observables. That means that there can be states where both observables have definite values at the same time. But if two measurement operators do not commute, then they are incompatible observables. Measuring one generally changes the state in a way that destroys definite information about the other. So the commutator is basically a test for compatibility that asks if the order of quantum operations matter. If that answer is no, then the commutator is 0. And if that answer is yes, then the commutator is non-zero. And in quantum mechanics, this is a huge deal, because when two operators commute, they can share the same eigenstates. And if they share the same eigenstates, then a state can have definite values for both observables at the same time. And if they don't commute, they generally cannot share a complete set of eigenstates. So a state cannot have perfectly definite values for both observables at the same time. Now that's the deeper mathematical reasoning behind uncertainty. So it's not that our instruments suck at measuring multiple axes of magnetization, it's just how operators are. Now let's apply this over to spin. For spin 1/2 nuclei, the spin angular momentum operators are Ix, Iy, and Iz. These are the operators for measuring spin along the x, y, and z axes in units of h-bar. Now if we want to know whether we can measure the x component and the y component at the same time, we can ask whether the Ix and the Iy operators commute. The commutator is Ix, Iy minus Iy, Ix. So we need to calculate two products. First, for Ix, Iy, we can pull out the constants of 1/2 to the front and get 1/4 times the product of these two matrices. Now when we multiply row by column, we'll get 1/4 times the 2 by 2 matrix of I0 and 0, negative I. Now we calculate the opposite order of Iy, Ix. We'll start again with the same thing and pull out the constants to get 1/4 in the front. Multiplying row by column again, we'll get 1/4 times the 2 by 2 matrix of negative I, 0, 0, I. Now plug both products into the commutator. When we combine these matrices, we'll get 1/4 times the 2 by 2 matrix of 2i, 0, 0, negative 2i. Last step is to factor out the 2. And if you don't recognize it, we get the IZ operator with an I in the front. So that means the commutator of Ix, Iy is equal to I times the operator of Iz. And this is one of the commutation relationships. We did Ix, then Iy, and got this matrix. But when we did Iy and then Ix, we got this matrix. Those are not the same matrices. Cool side note though, they're actually Hermitian conjugates of each other. But anyways, this says the order matters. And because the order matters, the commutator is not 0. That's what it means to say that the Ix and Iy do not commute. Physically, this means that spin along the x and spin along the y are not simultaneously definite observables. A state can be an eigenstate of Ix, or it can be an eigenstate of Iy, but it cannot be a definite eigenstate of both at the same time. Now, the fact that we get I times Iz on the right side is not random at all. It's telling us something about the geometry of angular momentum. When we calculated the commutator of Ix and Iy, we were asking what is the difference between doing an x spin operation followed by a y spin operation versus doing a y spin operation followed by an x spin operation. And what is that difference? A third direction z. So the commutator of Ix and Iy is defined as I times Iz. This means that the failure of Ix and Iy to commute has the structure of a z-axis operation. In other words, when you swap the order of x and y operations, the mismatch between those two orders behaves something related to Iz. I know this sounds really weird, but I'm sure it'll make perfect sense when we use rotations, which you may already be familiar with. In ordinary 3D space, rotations about different axes generally don't commute as well. The operators for rotation are these three right here, the Rx, Ry, and Rz, and these need to be fully unpacked later, but for now, just know that each describes a rotation about the x, y, or z axis. So forget about Ix and Iy right now. Let's visualize what happens for this Rx and Ry commutator for 90-degree rotations. Oh, by the way, it's good convention to draw your axes like this, with the z pointing up, x coming towards you, and y going in the plane. Going by the unit circle, rotations are counterclockwise, so drawing it this way will help with understanding why we get certain directions after certain rotations. Alright, going back now, I want you to focus on these two pencils. I'll apply the first order combination to the left pencil, and the second order combination to the right pencil. First, we rotate it by 90 degrees about the x-axis, then we rotate it 90 degrees about the y-axis. This pencil will end up pointing in the negative y direction. For the second one, we rotated 90 degrees about the y-axis, then we rotated 90 degrees about the x-axis. This pencil will end up pointing in the positive x direction. And if you look closely, the difference between these two orders is exactly a 90-degree rotation about the z-axis. Applying the same logic, if we compare x and y, the leftover direction is z. If we compare y and z, the leftover direction is x. And if we compare z and x, the leftover direction is y. That repeating pattern gives us a cyclic structure. It follows the cycle of x to y to z, and z back to x. So the commutator of the first two directions gives the third direction. And if you reverse the order, the sign flips. For example, the commutator of Iy and then Ix is equal to negative I times Iz. With the pencil analogy, it's now the difference between pencil 2 and pencil 1. So to get from 2 to 1, it's a negative 90-degree rotation about the z-axis. This sign flip is another indicator that tells us that the order does matter. Doing x then y is not the same thing as doing y then x. So back when I said that the failure is connected to z, I didn't mean that measuring x and y literally produces a z measurement. I meant that the mathematical mismatch between x and y operations has the form of the z operator. That's the angular momentum algebra telling us that spin components are tied together geometrically. This means that the three components are not independent quantities. They form one linked structure. And that linked structure is what makes spin angular momentum behave like angular momentum. This cyclic structure here is one of the most defining signatures of angular momentum. One quick side note, here we've been using Ix, Iy, and Iz in units of h-bar. If we include the h-bar inside the operators themselves, then the commutator is written as these three right here. But in spin dynamics, it's very common to work in units of h-bar, which is why we can just write the cleaner version like this. I'm sure what'll solidify the concept of commutation is seeing how it applies to our understanding of eigenstates and expectation values. If we allow Iz to operate on alpha, it's going to give a plus h bar over 2 and only a plus h bar over 2. But if we measure Ix on alpha, we don't get one guaranteed value. By multiplying these matrices, we can see that we actually get 1/2 times beta. This is because alpha is not an eigenstate of Ix, so we're not just going to get alpha back with some eigenvalue in the front. Instead, alpha can be written as a superposition of the eigenstates of Ix. We can write it as the sum of two column vectors, 1, 0 and 0, 1. And these two column vectors correspond to the plus x and the minus x states. So now getting an x measurement would mean applying Ix to alpha, but alpha as the superposition of plus x and minus x. If we do that, then we'll get a 1/2 in front of the plus x state and a negative 1/2 in front of the minus x state. And just so we're not confused about the numbers in front of us, the 1 over square root of 2's are just the probability amplitudes, and the 1/2 and the negative 1/2 are the eigenvalues that we measure. So the true measurements will give us either a plus h bar over 2 or a negative h bar over 2. Each has a 50% chance when we square the probability amplitudes. And just to be clear again, this isn't because alpha is secretly pointing in both x directions and we just don't know. The state is simply not possessing a definite x spin value before that measurement. This becomes clear again when we take the Ix expectation value of the alpha state. We get 0 because the average measurement after equal probabilities of plus h bar over 2 and negative h bar over 2 is effectively 0. Now let's make this order issue a bit more physical. Imagine a spin starts in the alpha state, so that means it's definite along z. Now let's say we measure Ix. Because alpha is not an eigenstate of Ix, the measurement can either give the plus x result or the negative x result. And after that measurement, the state is projected into the corresponding x eigenstate. So let's say we flip that coin and we got the result of plus h bar over 2 along the x. The state will now become the plus x state. Wait, but now that spin is no longer alpha, so that means it's no longer definite along z. So if we measure Iz, we may get alpha or beta for the same reason as before. Now I can show you this by writing the plus x state in terms of the alpha and beta eigenstates of Iz. The 1 by 1 column vector can be written as the sum of a 1 by 0 column vector and a 0 by 1 column vector, which are alpha and beta. Now applying Iz to the plus x state is applying Iz to the superpositions of alpha and beta. And we know that when we apply Iz to its eigenstates, alpha will give us a 1/2 and beta will give us a negative 1/2. And this means that we can either get a plus h bar over 2 or a negative h bar over 2 along z. This means measuring x changed what we can later say about z. The measurements interfere with each other because the operators do not commute. That's the physical meaning of saying that the commutator of Ix and Iz does not equal 0. The order of the measurement matters. Measuring z then x is not the same thing as measuring x then z. Now comparing that with operators that do commute, measuring one does not destroy the definiteness of the other. They can have shared eigenstates. So if a state is an eigenstate of both operators, measuring one still leaves the system in a state where the other has definite value. That's why commutation is one of the most important concepts of quantum mechanics. It tells us which physical quantities can be known together. All of this just to say that measuring Iz projects the spin into an eigenstate of Iz, and that post-measurement state is generally uncertain with respect to Ix. And vice versa as well. Measuring Ix projects the spin into an eigenstate of Ix, and that state is generally uncertain with respect to Iz. Now, bringing this back once more, the Bloch sphere is actually an exceptional model for understanding this. On the Bloch sphere, a pure spin 1/2 state points in one definite direction. If the state points along z, it's either alpha or beta. If it points along x, it's either plus x or minus x. And if it points along y, it's either plus y or minus y. But the Bloch sphere can sometimes be misleading if we take it too literally, because the vector that you're seeing here on the Bloch sphere is not a classical arrow with simultaneously definite x, y, and z components. It represents expectation values. So the components of that Bloch vector are the expectation values of ix, iy, and iz. For a pure state, the Bloch vector tells us the average spin direction we would observe after many repeated measurements. But it does not mean that one individual spin has definite measurement values for ix, iy, and iz all at once. That distinction matters a lot. For example, using the expectation value formulas here, the plus x state has these values. Ix is 1/2, Iy is 0, and Iz is 0. This means that repeated Ix measurements give plus h bar every single time. But repeated Iz measurements give plus h bar half the time and negative h bar half the time. The average z value is 0 because of this, but a single z measurement never gives you 0. And this is the same for y. So again, the Bloch sphere shows expectation values, but not definite measurement outcomes simultaneously. And non-commutation is the reason those two ideas are different. Now in NMR, this becomes extremely important because later we will see that spin dynamics is built from operator evolution. When a spin evolves under a very important operator called the Hamiltonian, whether that Hamiltonian commutes with the spin operator determines whether that spin component is conserved or changes in time. For example, if the Hamiltonian commutes with Iz, then the z component of angular momentum is conserved under that evolution. And if the Hamiltonian does not commute with the Ix or the Iy, then the transverse components can either evolve, rotate, or precess. This is exactly the kind of logic that's going to let us understand chemical shift evolution, J-coupling, RF pulses, and eventually pulse sequences. Because in spin dynamics, we will constantly be asking questions like what operator is acting, what does it commute with, and what does it transform? So commutation gives us those answers by telling us if those measurements are compatible. It tells us when order matters, it tells us which quantities can be simultaneously definite, and later it will tell us how spin operators evolve under Hamiltonians. So in summary, if two operators commute, their order doesn't matter, and their observables can be defined at the same time. If two operators do not commute, their order does matter, and measuring one generally destroys the definiteness in the other. For spin 1/2 nuclei, the three spin components do not commute. And that is why we cannot say that spin has definite x, y, and z values all at once. The spin state can have expectation values along all three axes, but definite measurement values only exist for the operator whose eigenstate the system is actually in. That difference between expectation values and definite measurement outcomes is one of the keys to understanding quantum spin dynamics.